Have you ever looked up at the night sky? You see a blanket of tiny twinkling lights. Each light is a star, a sun like our own, but incredibly far away. For thousands of years, humans have stared at these stars. We have wondered what they are. We have asked what secrets they hold. We use our eyes, but our eyes are small. They can only gather so much light. To see more, to see farther, we needed something better. So we built telescopes. These amazing instruments act like giant eyes. They collect more light than our pupils ever could, making faint objects appear brighter and distant things seem closer. Galileo Galilei pointed his small, simple telescope at the heavens. He saw the moons of Jupiter. He saw the craters on our own moon. He changed our view of the universe forever. The solution seemed simple enough at first. If you want a sharper image, you just need to build a bigger telescope. So we built them. These colossal structures house mirrors that are many meters across. They are engineering marvels, designed to gaze into the deepest reaches of space. With them, we have discovered distant galaxies. We have watched stars being born and dying. We have mapped the vast structures of the universe. But even these giants have their limits. There is a physical boundary to how large we can build a single solid mirror. They become too heavy, too expensive, and too difficult to shape with perfect precision. The universe is vast beyond our imagination. The secrets we want to uncover are incredibly small from our perspective. To see such things, you would need a telescope the size of a city, or maybe even the size of a whole continent. Building a single mirror that big is simply impossible with our current technology. When faced with an impossible problem, scientists often get creative. They look for a clever workaround. They find a new path forward. If you cannot build one gigantic telescope, what is the next best thing? The answer was surprisingly elegant. It was a solution that did not rely on making one massive piece of glass. Instead, it used a trick. It combined the power of many smaller telescopes. This technique is called interferometry. It is one of the most powerful tools in modern astronomy. It allows us to build a virtual telescope that is much, much larger than any single telescope we could ever construct on Earth. Imagine you have two small telescopes. You place them far apart from each other, let's say a few kilometers apart. You point both of them at the same distant star. Each telescope collects the light waves coming from that star. The key is that the light waves will arrive at each telescope at a slightly different time. This tiny difference in arrival time contains precious information. By carefully combining the light from both telescopes, astronomers can reconstruct an image. It is as if they were using a single giant telescope. The size of this virtual telescope is determined by the distance between the telescopes. One of the most famous and iconic examples is the Very Large Array, or VLA. It's a stunning collection of 27 enormous radio antennas, each one 25 meters wide, standing like sentinels in the high desert plains of New Mexico. The genius of the VLA lies in its flexibility. The 27 antennas aren't fixed in place. They're mounted on a railway system laid out in a giant Y shape. Special transporter vehicles can pick up these 230-ton dishes and move them to different positions. Inside the central control building is the correlator, the supercomputer that acts as the heart of the VLA. This machine performs the trillions of calculations needed to compare the signals from every possible pair of antennas. To see even more detail, astronomers needed to go higher. Welcome to the Atacama Large Millimeter Sub-Millimeter Array, or ALMA, perched at an astonishing 5,000 meters above sea level in the Atacama Desert of northern Chile. ALMA is the highest large telescope on the planet. ALMA is an interferometer, but it is a far more advanced and sensitive one than the VLA. The surface of each ALMA dish has to be accurate to the width of a human hair. The timing and data processing systems are on a whole other level of complexity. ALMA's most famous discoveries have been its breathtaking images of protoplanetary disks. For the first time, ALMA could see the dark gaps and rings in these disks, which are the clear signposts of new planets carving out their orbits. For a century, black holes were creatures of mathematics and imagination. They were predicted by Einstein's theory of general relativity. These are objects so dense, with gravity so strong, that nothing, not even light, could escape their grasp. This monumental task was taken on by the Event Horizon Telescope collaboration. The EHT is not a single telescope, but a planet-wide network of radio observatories, all linked together, using very long baseline interferometry. In April 2019, the world held its breath. The EHT team released the result of their years of work. It was the image, a glowing, lopsided ring of light surrounding a perfect circle of darkness. For the first time in history, humanity was looking at the shadow of a black hole. Where did we come from? How did our own planet, Earth, form? For a long time, the answers were hidden from us, shrouded in thick clouds of dust and gas. We knew that stars and planets form together from vast, cold molecular clouds that collapse under their own gravity. In 2014, ALMA delivered one of its most famous images. Instead of a smooth, uniform disk, ALMA revealed a stunning series of concentric rings and dark gaps, looking like the grooves on a vinyl record. This was the smoking gun that astronomers had been looking for. Each gap in the HL Tauri disk was likely the location of a newly formed planet, still in its infancy. For the very first time, we were not just guessing about planet formation, we were watching it happen. It was like having a sonogram of a new solar system being born. The success of interferometers like the VLA, ALMA, and the EHT has only made astronomers more ambitious. The answer is simple. We build even bigger and better arrays. This next great leap is already underway. It is called the Square Kilometer Array, or SKA. The SKA will not be a single observatory in one location. It will be a colossal instrument with antennas spread across 2 continents. One part will be built in the remote desert of Western Australia, the other across southern Africa. This incredible sensitivity will open up entirely new frontiers of discovery. The SKA will be able to detect the faint radio signals from the very first stars and galaxies that formed after the Big Bang, a period known as the Cosmic Dawn. Another, even more audacious idea is to take interferometry into space. Imagine 2 or more spacecraft flying in precise formation, hundreds or even thousands of kilometers apart. Each spacecraft is a telescope. Together, they would act as a single, giant virtual observatory. One idea is to build a space-based optical interferometer to search for Earth-like planets around other stars. It could not only take a picture of a pale blue dot orbiting a distant sun, but it could also analyze the light from that planet's atmosphere, searching for the telltale biosignatures of life. Building a space interferometer is one of the greatest engineering challenges we can imagine. The spacecraft would have to maintain their positions with millimeter precision while flying freely in space. The cost and complexity are enormous, but the scientific payoff would be equally immense. We began this journey by looking up at the night sky, a canvas of countless tiny lights. We learned that to understand this vast cosmos, we needed bigger eyes. For centuries, this meant building larger and larger single telescopes, colossal structures of glass and steel. But we hit a wall. Interferometry was that brilliant solution, a testament to human ingenuity in the face of cosmic-scale problems. By linking many smaller telescopes together, we learned to create a virtual instrument of incredible power. It is a technological symphony, where each separate instrument plays its part in perfect harmony. We have seen the shadow cast by a supermassive black hole, confirming a cornerstone of modern physics. We have watched as new solar systems are assembled from disks of dust and gas, giving us a direct look at the origins of planets like our own. The power of interferometry extends beyond the incredible images it produces. It has fundamentally changed our relationship with the universe and our place within it. Every new discovery brings the cosmos a little closer to home. Seeing worlds being born around other stars helps us to better understand the long chain of events that led to the formation of our own Earth, making our home feel both precious and perhaps less unique than we once thought. This ability to see with such clarity inspires a deep sense of wonder and humility. It speaks to the boundless potential of the human mind and our unyielding curiosity. The more we learn, the more we understand how much more there is to discover. The future of this technology promises even more profound revelations. The Square Kilometer Array will peer back to the dawn of time. Space-based interferometers may one day take a direct picture of another Earth-like world and search for the chemical signs of life in its atmosphere. As we continue to link our telescopes across deserts and continents, and one day, across the vacuum of space, we are also linking ourselves more closely to the cosmos we call home. Ultimately, interferometry is more than just a clever way to build a bigger telescope. It is a powerful expression of our innate human desire to understand where we came from and to see our place in the grand scheme of things. By combining the vision of many eyes into one, we create a perspective that is far greater than the sum of its parts.